The lab this week was about black holes and orbits. In this lab, we had two parts to complete. The first was to find the mass of a black hole based on known values, and the second was to try to get a rocket ship to travel in a figure-8 orbit around the moon and Earth. We used GlowScript to calculate the forces and create a model to visualize the orbits of the two parts. In both parts of the lab, the primary force used is gravitational force. This is modeled by Fg equals negative g big M little m over r squared times r hat. G is the gravitational constant, big M is the mass of one of the objects in the system, and little m is the mass of the other object in the system. R is the magnitude of the radius between the objects, and r hat is the direction. For the black hole, we also included values of Fnet parallel and Fnet perpendicular for additional calculations. For the rocket problem, we used the above equation in various implementations, as well as velocity and position update formulas. As mentioned earlier, the goal was to find the mass of the black hole. To do this, we determined how we would find Fnet if we knew the mass of both objects, which in this case was the black hole and the star. Then we worked backward from there, rearranging the formula to set the mass of the black hole equal to an equation with known values. From there, it was just plugging in the known values to solve for the mass of the black hole and creating a model of the orbit. The three different equations used relating components of force were Fnet parallel, Fnet perpendicular, and the total Fnet. To find these three components, we used the code below to calculate different parts of each force, then used them to find the mass of the black hole. And for the code, we found the initial and final velocities and momentum, and then from there found the changes in each value to get the net force. And then from there, it was finding the parallel and perpendicular components of the change in momentum over the change in time, which we could then use and substitute into the net force components. For trying to get a figure-8 orbit, we needed to estimate the initial velocity in the x and y directions. We used the gravitational force equation for two different forces. To do this, we used three different net forces: the force of the planet on the moon, the force of the ship on the moon, and the net force on the moon. Then the velocity and position update formulas were used to create the model. For the first two forces, we used the gravitational force formula, then set the net force on the moon equal to the force of the planet on the moon, and added the force of the ship on the moon. One problem that did occur though was trying to get a neat figure-8, so the image shown next is the closest we could get. The gravitational force formula, we used known values again to calculate the unknown force. We needed to calculate the magnitude and direction of the distance between the designated objects, which in this case we had the Earth, the Moon, and the rocket ship. And then we plugged those values into the formula. The code on the left shows the process done to accomplish this. And then once we had the net force, we used the appropriate velocity and position update formulas to be able to create the model, which the code for the force is on the left, the code for the velocity and position update is in the middle, and then the final orbit that we were able to get is on the right. If we were to have a system with a black hole, a star, planet, and a moon, we would need to include several different forces. We would need Fnet on the moon by every other object, Fnet on the star by every other object, Fnet on the planet by every other object, and Fnet on the black hole by every other object. The magnitude of the predominant force would be whichever has the greatest mass and the shortest distance between the objects, between every other object. But if there isn't a huge difference between mass and distance between all of the objects combined, they would all act relatively equally on each other. And for the black hole problem, we use perpendicular and parallel components of net force. This is different from the components of the momentum though. A change in momentum is a change in velocity, while the change in the net force is the change of momentum over change in time. So the change in force would be equal to how much the change in velocity is changing in both magnitude and direction over the designated time slot.